80 was done. Let's go to 81. Prism 1 of mass m1 and with angle alpha, so 1.23, that is this figure, rests on horizontal surface. Bar 2 of mass m2 is placed on the prism. Assuming the friction to be negligible, find the acceleration of the prism. Oh, so there's no friction. This bar is on that. Okay, fine. This prism should be like moving. Okay, fine. Just normal forces acting on it. It rests on the horizontal surface. Oh, it just placed and then fine. The bar 2 is just placed and then it's released. Fine. Good. It's doable. So what do we have? Yeah, fine. Let's do this thing. So you got a normal force acting on like that, right? This angle is alpha. This angle will be alpha. Then this will be 90 minus alpha. Just got n cosine of 90 minus alpha, which will be n sine alpha. So n sine alpha is equal to this guy's acceleration, whatever that is, in this direction, right? Exactly. So yeah, I mean you could do that, of course. So we'll just say it's equal to whatever capital M is. So capital M is the mass of 1, that times the acceleration of this guy in that direction. Now let's figure out what the acceleration of 2 should be, so that, or in fact let's not do that. Yeah, right. Let's go for 2. So for 2, first of all, if this is moving with a in this direction, then what's the component of this acceleration that's normal to the surface? This angle is 90 minus theta, so what we are looking for is another cosine of 90 minus theta added to it. So it has to be n sine squared alpha. So you can say, okay, n sine squared alpha is equal to mass times a normal. That is the acceleration perpendicular to this surface, right? Let's figure out the acceleration of 2. So it's small m mass. You got g acting on it, right? So you got g sine theta in this direction. So g sine alpha. You got g cosine alpha and everything. Yes, you also got the normal force acting on it. So you got n upon m in this direction, and you got g cosine alpha in this direction. Exactly. So what will be the acceleration perpendicular to this surface? It will just be, so in this direction particularly, that's going to be g cosine alpha minus n upon m. This has to be equal to this thing, so n sine squared alpha. Oh, sorry, n sine squared alpha upon capital M. Sorry, that should be the thing. Just got g cosine alpha is equal to n into sine squared alpha upon capital M plus 1 upon m. From here you can figure out what capital N should be, and what we actually want is the acceleration of the prism. So of 1, that is this a, that will be capital N upon capital M times sine alpha, right? So yeah, I just want upon capital M, so you can say capital N upon capital M into sine squared alpha plus, so capital M upon small m, we'll call that as eta, and that will be equal to g cosine alpha. So this quantity will just be equal to g cosine alpha upon sine squared alpha plus eta. Now what do we want? We just want, yeah, exactly that thing, capital N upon capital M, but that thing times sine alpha actually. So this should be this times sine alpha. That's it. That's the acceleration of prism 1, right? That will be in the horizontal direction and everything. I guess that makes sense. Yeah. Okay, cool. So 81st done will be this thing, g sine alpha cosine alpha upon sine squared alpha plus eta, which is basically just capital M upon small m. Right. Next, 82. In the arrangement shown in the figure 1.24 is this figure 5. The masses m of the bar and capital M of the wedge, as well as the wedge angle alpha, are known. Okay, this angle is known, these masses are known. The masses of the pulley and thread are negligible, the friction is absent. Find the acceleration of the mass capital M. Fine. So alright, so you got tension over here, you got tension acting in this direction and then in that direction. Well, it can only move horizontally, so yeah, fine. It's doable, not complicated. Okay, this is, huh. Hey, what if we think about the whole system moving? No, okay, that's the Think about it. If this is moving, so this wedge is moving like this with some acceleration, then it's moving in this direction with how much acceleration? Just like we did before, this angle should be alpha, so this angle will be 90 minus alpha. So then this will be a sine alpha, right? So this thing is moving with a sine alpha in that direction. What about small m? Well, it's also moving with a sine alpha in that direction, right? So we don't know anything about what's happening in this direction, yes, but we do know that these are moving with a sine alpha and a sine alpha, both of them same acceleration. So you can say, okay, small m plus capital M times a sine alpha, that will be, no, because the normal, so the ground is also applying some force. So we have to do the proper analysis for this. You can't apply a shortcut right away. Fine. So let's draw FPD for small m. So you got what? Tension force in this direction. You have mg sine alpha in this direction, mg cosine alpha in this direction. And then you got normal force acting on this. Let's talk about this wedge. So you got, okay, we should not say it's like F, it's just T. So now you got T acting in this direction. Yeah. Hey, I mean, think about it. No friction is there. The gravity, is it doing work? I think it is doing work. Right. Gravity is doing work. That's a problematic thing. But the tension is not actually doing any work, is it? No, it's not. You could use the fact, okay, no, just do it the normal way. Tension in this direction, tension in that direction, right? So the component of this tension, yeah, need to figure about that. No, in fact, we'll just figure out the horizontal acceleration first, because that's the essential thing. So this angle is going to be alpha, right? Any other force, of course, the normal force, this direction. This angle is alpha, right? Fine. Any other thing? Nothing, right? Okay, cool. So let's do it. Let's write the equation for capital M. So normal cosine of 90 minus alpha is normal sine alpha plus tension minus tension cosine alpha. This thing will be our mass times whatever acceleration of this mass is. So that acceleration times sine alpha will be the acceleration perpendicular to the surface, right? Okay, perfect. And let's also write the equation for this thing. So yeah, right. I mean, this is a sine alpha in that direction. You don't know what this string constraint, right? Yeah. So if this has acceleration in this direction A, and its acceleration in this direction is, wow, this is weird. So it has a component of acceleration in this direction and a component in that direction. It's kind of complicated, right? What I'm thinking is we could maybe apply the string constraint, right? So we know it's gonna slide down, and how do we do this? Oh, what we could do is, because this guy is moving with acceleration in this direction, we could apply a pseudo force on this, and then will be completed in the frame of capital M. And then this guy's acceleration in this direction, that will be exactly what we are looking for the rate of change of this thing. Exactly. So it's gonna be A in this direction, right? Wow, if this, what's this? This is so complicated, right? Yeah. And then of course, with respect to this capital M, nothing's actually, I mean, it's not moving in this direction at all. So that's nice. So you got the first equation like that, huh? Then you will also have normal is equal to, so normal plus A times, come on. This angle is supposed to be alpha, so it's gonna be A cosine alpha in that direction, right? It should be MA force. So you will just have normal plus MA, this angle is alpha, is supposed to be what? Sine alpha, right? So MA sine alpha is equal to, nothing else is over there. So like mg cosine alpha, just like that. That's another equation. This is an equation, and the final equation will be the fact that with respect to capital M, this should be going down by acceleration capital A, right? So you will have mg sine alpha. Wow, this is very weird. Okay, plus ma cosine alpha. Uh, yeah, that minus tension is equal to ma. That's the third equation. So now let's tidy up everything. Okay, now think about it. What do we do with this? So we don't want A anywhere, right? No, in fact, we don't want T anywhere. We want to eliminate T first of all. So over here, you got this T. You can just put that in there, right? Exactly. And then you can also find what n sine alpha is. So we'll do that. N sine alpha is equal to mg cosine alpha sine alpha, that minus of ma sine squared alpha. This is one of the equations. And from here you can say, okay, tension is just equal to mg sine alpha plus ma cosine alpha minus ma. This is another equation, and then we don't need these equations anymore because it's the same thing as that. And we'll put these things in here, and let's see what we get. So this plus this times of 1 minus cosine alpha. Wow, this is some complicated thing. So t into 1 minus cosine alpha, what will that be? Oof. So this will be what? Mg into, so sine alpha into 1 minus cosine alpha, just sine alpha minus sine alpha cosine alpha, and then plus ma into so it's got, yeah, negative over there, so like it's supposed to be negative ma 1 minus cosine alpha squared, like that, which makes sense. And this thing can be written as, so it's already simplified enough, fine. And then you just add these, so this plus that is mg sine alpha, and this plus that, oof, it's minus ma into, let's see, sine square alpha plus cosine square alpha 1, then 1 plus 1 2 minus of 2 cosine alpha, right? And all of that will be equal to capital M times small a. That does it. So you will find out acceleration through this thing. Easy, right? Okay, so this is our final equation that we care about. We don't care about any of these things. Alright, cool. So we'll divide by small m and call capital M upon small m as eta. So this will be g sine alpha minus 2 times of acceleration into 1 minus cosine alpha. Yes, yes. Plus cosine alpha squared, and then you got sine squared alpha, which is like 1 minus cosine alpha. Wait, yeah, it should be just that. Exactly. And then this is equal to eta times a. So it's got a into eta plus 2 times of this, like 2 minus of 2 cosine alpha is equal to g sine alpha. So it's got acceleration is equal to g sine alpha upon eta plus 2 minus 2 cosine alpha. That should do it. Yes. Where of course eta is equal to capital M upon small m. Next question, 83. Particle of mass m moves with along a circle of radius capital R. Find the modulus of the average vector of the force acting on the particle over the distance equal to quarter of the circle. Mass m moves along circle of radius R. The modulus of average vector of force acting on the particle. You mean the average vector? So it's like just acceleration times the mass. Average acceleration, that is. So fine. Over the distance equal to a quarter of the circle. I mean, it's very doable. So okay, you got these different things. So uniformly and with constant tangential acceleration or whatever. Yeah, whatever. You know what? We'll do B. We'll do B and then just put A equal to zeros to get A basically. So constant tangential acceleration, call this thing A. Then what do we have over here? Over here, this thing is, let's say, going with U, right? And now over here, because it's constant tangential acceleration, that will basically du tangential upon dt. Exactly. So now it will be the tangential velocity will be u plus uh, u plus a delta t. So what's delta t though? Now you can use v square minus u square equal to 2s, right? Because tangential acceleration is constant and everything. So it's doable, I guess. Yeah, I mean, what was the thing once again? V dv is equal to uh, what was this? A vector dot d s vector, something like that. So that was just a tangential times ds, and then integrate these things to get the thing that we want. So yeah, right. You don't know what a time required is. Uh, yeah, I mean, like how I'm supposed to find. Okay, don't do that. Don't find. This thing is v. Just know that v square minus u square is equal to 2 times of and tangential extension. Let's say that thing is a, and this s will just be equal to 2 pi r upon 4. So pi upon 2 times r, where this is the radius r, which is basically just pi a r, right? So now you know what v squared is. What is the modulus of the change in velocity? So you got v in this direction and then negative u in this direction. So v u magnitudes, and this vector, this will have magnitude of square root of v square plus u square, which will be square root of. So v square we already know, right? It's just pi ar plus u square. So it's going to be pi ar plus 2u square. Exactly. And this thing upon time required, of course. Oh no, we do require time. Oh, now I'm supposed to find the time out. So its speed is increasing linearly. That's all we have to use. So you can say, okay, s is equal to v plus half t square. That might work, right? So you will say, what's the s thing once again? Pi upon 2r is equal to ut plus half at square. And a is just that. So like, yeah, of course. What is the quadratic? I don't want to solve that. Oh, come on. Okay, where did it go? We want to find the modulus of average vector of force acting on the particle. Okay. If this was constant velocity, it would have been a piece of cake, but it's not. So you got to find what t is, otherwise it's not solvable. Oh, come on. You really can't do anything, can you? Okay, time to do it. So you have to divide this by t. I need to figure out what t is through this equation. It's the worst. At squared plus 2ut minus pi r is equal to 0. So we'll just have t is equal to minus p. So minus 2u. Oh, come on. This is not going to help much. Okay, minus 2u plus minus square root of b square. So like 4u square minus 4 is so plus 4a by r, and that upon 2 times of a, that should do it. So t is just minus u upon a, or let's just not do that, minus u plus minus square root of u squared plus a pi r, and that thing upon a. Right, now which of these, plus or minus? The plus one, of course, because negative won't do anything. It's like, how can it be negative time? It has to be positive. Okay, this is nice. So you just need to divide by that. Doesn't look good though. So you divide by that thing. Come on. The square root of u squared plus pi a r. Okay, minus u. What is this? And that thing upon a. So maybe like rationalize the denominator. Maybe. First of all, divide. So it's gonna be like that. Yeah, we could rationalize the denominator. Why not? So when we do that, it will just be pi r in the denominator. So pi r square root of pi a r plus 2u squared, and then all of that times square root of u squared plus pi ar plus u. This is the time required. Should be doing it. Sorry, this is the acceleration. Sorry. So yeah, we got thing. So this times force. Sorry, this times the mass. That will be our average force. So I'm just gonna put that there. And did they say use V or U? Wait, what? They said that the initial velocity is equal to. Oh, I didn't read all of that, did I? Fine, but you got a very, very general equation for. Okay, but this is just a quarter circle. It is not that useful actually. So we'll just say put u is equal to 0. So you have b done in that case. B is just m square root of pi a r, and this u is now 1. So it's just, yeah, square root of pi a r upon pi r. Then you got, what's this thing, square root of pi a r. So it's like it's pi a r upon pi r, which is just m times a. This is what is this? But how can that be? No, this is not good. How can that be? I get it that initially it was just 0, so finally it's b, right? I mean, yeah, I understand what happened, but come on, seriously. I did all of this and now just give me this. I'm gonna keep it over there, in fact. And hey, you know what? Since we have that pi a r over here, I mean, like, what does that represent? This represents, uh, yeah, that kind of represents 2as everywhere, doesn't it? So what if we go for some general theta? Then instead of having pi a r, what we'll have is, so 2as, 2 times a times s will just be 2 pi upon theta times 2 pi r. Well, okay, sorry, which will just be r theta. That would do it. So yeah, of course. In this particular case, theta was just pi upon 2, and that's why it was pi ar. Now this will just be 2 ar theta. We can put that in there, and that will give us a more general form for this. Okay, fine. So this will be mass. Just actually write it down. Average acceleration, the magnitude of that thing, that will be square root of. So instead of having pi ar, what was this? 2 ar theta. Yes. So 2 ar theta plus 2u squared upon pi times r. Instead of using that, I'll just say 2r theta. Yes. And that times square root of u squared plus 2ar theta, right? And I think plus u. That should do it. This is what we found out through this example. Okay, so now we don't need this anymore. So hey, it's just mass times acceleration, and then oh, it's like this. These two conditions are in fact very different. So in this case, acceleration will be 0, so you can just cancel these terms out. So then this will be square root of 2u squared upon 2r theta, square root of, well, this is gone, so like u squared 2u, of course. So it's just equal to this thing, u upon r theta into square root of 2u squared, whatever. That will just be equal to, well, u squared, this the square root 2, u squared square root 2, and then upon r theta. That should do it. Yeah, which makes sense because r theta is the length and that upon u is the time required. So u square root 2, the difference that upon that, of course. Why did I do all of this? It was so simple. Okay, we got a general expression. It's good, right? Okay, so you got the thing. Now they're saying it's going with uniform velocity v, so it's just make this thing. And theta is just pi upon 2. So r pi and then 2 gone. So 2 square root. say pi r. This will do it. Okay, next. So go to the next page. 84th. 84th is an aircraft loops the loop of radius r is equal to 500 meter with a constant velocity v is equal to 360 kilometer per hour. Find the weight of the flyer of mass 70 kg in the loop, upper and middle points of the loop. Sorry, in the lower, upper and middle points of the loop. Wait, weight of what? Flyer of mass 70 kg. You don't have a figure for this, do you? No? Flyer. I don't know what that means. Is that a pilot or something? Wait, what? What do you mean by lower, upper, and middle points? So this loop is not horizontal; it's vertical, I think. Oh, okay. So it really is just vertical. Well, this is different. Fine. So then the weight of anything in that plane. How you find that out? So, for example, if the plane is, so we'll just say, okay, plane is something like a box. I know it's very absurd, but that's how we will think of it. And there's some object in it. You want to find the weight, maybe there's some scale over here or whatever. What's the normal force put on this object by the plane? That's what we need to figure out. So because this plane is going like this, the object is also going like that, right? So there's no such tension or anything pulling it up. There's just normal force pulling it up and gravity pushing it down. So basically it's just an object that is going in a circular motion, and you need to figure out what the normal force on this at any point is, right? So this is this gravity acting on it, and that's also the normal force. So wait, when this goes oh, this is very weird. So understand over here it's just going like this, right? Yeah, it's supposed to be this kind of acceleration, and that's why there's this normal force. Over here it's gonna go up, this object, right? It's getting a constant g force in this direction, yes, and the tangential acceleration should also be 0 all of the times, right? Exactly, because it should not accelerate anyhow. So this is just g force pointing in that direction, and at the same time there's this normal force. So it's it has many components in this case, because there's also normal force required for it to be in the circle, and then you have to cancel away this thing because no tangential acceleration. This is so complicated. So this will be different at different angles, right? Oof. So you want to find the lower, middle, and upper points, right? So let's do the lower point first. When we say weight, we do mean the magnitude of the normal force. That's what will be the weight. Yes. All right. So, it's just normal. The lower point first. So this thing, this object is needs a centripetal acceleration in this direction, which is provided by the normal force, and then there's gravity acting on it. So this is going to be mv squared upon r. What is it? It's moving with v, right, upon r, and this thing is small m, whatever. It's got mg in this direction. This is normal force. So it's got normal force is equal to mg minus mv squared upon r. That should be doing it. There's no tangential acceleration whatsoever. This will be doing it. So the weight is just mg minus mv squared upon r. Okay, let's go for the middle section. So for the middle points, yeah, this object going up, so the normal force, sorry, the centripetal acceleration required is like this. So it's still just mv squared upon r because it's v is not changing. Then there's gravity acting in this direction, so mg. So you should have mg in this direction as well. So this is part of the normal force. Is part of the normal force. This thing is actually required. Uh-oh. Uh-oh. That's not how it's supposed to be. It's supposed to be plus, because it would be n minus mg is equal to mv squared upon r. Right. I shouldn't draw it like that. Maybe draw the centrifugal force and whatever. Anyway, and then the normal force. So a component of it is in this direction. At the same time, we also need this force. So this combined, these two combined are the normal force. So the magnitude of this thing will just be m square root of v power 4 upon r squared plus g squared. That should do it. So middle, the weight is just m square root of v power 4 upon r squared plus g squared, whatever. And in the upper point, what happens? So now the gravity is actually helping it. So just got mg downward, we got normal force. Is it supposed to be upward or down? I mean, it's just the what do we say? It's just the what am I saying? The magnitude of the normal force that we have to look at, right? So you would need a normal force in. I don't know, maybe it's upwards. And then yes, like mg minus normal force is equal to mv squared upon r. So normal force is equal to mg minus mv squared upon r, right? The magnitude of that thing, because it could be up or it could be down. Hey, so over here it should no, okay, over here you don't have to put magnitude because it's yeah, but in this case you might have to put it. So upper is just magnitude, so m magnitude g minus v squared upon r. That should do it. So 84th done. 85th. Okay. Oh, we have to calculate this, huh? I'll leave that to you people. Okay, whatever. Just calculate this. So let's go with mg plus mv squared upon r first. What is m? 70 kg. So 70 times well, g will just take it to be 10 plus v squared upon r. So well, first of all, just figure out what v squared upon r is. V squared upon r is so v is 360 kilometer per hour. That is 36 into 10 power 4 meter per 10 per 36 100 seconds. So oh come on, that will be 100 meter per second, I think. Yeah, that should do it. Yes, that should do it. So it's just 100 meter per second. And that thing squares like it's 10 power 4, and that upon r. R is 500. Are you serious? 500 meters. Oh, okay, it's meters. Sorry, I thought it was like centimeters. Fine, so it's meters. So it's gonna be upon 500. There we go. So this will be 10 into 1,000. So it's got 20 as the thing. So v squared upon r is 20, right? So this thing is just gonna be 10 plus 20. There we go. So it's like 30 to 70. That is 2100 over here. It's still weird. I mean, 70 kg body, 2100 newtons. That's quite a lot, isn't it? It would have been say 700 meters. Okay, it's not. It's comparable. Fine. What about this guy? So it's gonna be m, which is 70 square root of, so I got 10 squared. Okay, and then 20 squared. So I'll take that 10 out. Square root of 1 plus 4. So 700 square 5. 5. Sorry. And then this thing. So let's do it. G minus, as I expected. Now this thing is negative. That's why I had to put that mod over there. So it's going to be 70 into 10 minus 20 is minus 10. So 700. Let's go to 85. A small sphere of mass, small and suspended by a thread, is first taken aside so that the thread forms the right angle with the vertical and then released. Any figure of this thing? No? Okay. Taken aside. Oh, so it was like this, and then you had to do it like that so that it forms 90 degree. Okay. So first taken aside that the thread forms right angle with the vertical. With the vertical or whatever. It's still the same thing. Okay. Suspended by thread, fine. The total acceleration of the sphere and the thread as a function of theta. Thank God it's theta and not time. Angle of deflection of the thread from the vertical. So from the vertical you say, so like in the intermediate, That it will be like this. That's what you're saying. So A is actually very easy. So you got, if it says mass M, it's like mg in there, and then you got tension right there, whatever. So this component, this angle is going to be theta, right? So you will just have, it's not, that's how, not supposed to be like that. This will be 90 degree, that will be 90 minus theta or anything. Oof. That's the vertical. This thing is also vertical. Oh yeah, of course. This angle is going to be theta. Then this is 90 minus theta. So mg cosine of 90 minus theta is mg sine theta basically. So like mg sine theta, that time over this length is the L. That is the torque on this system. That upon inertia, which is just mr squared. So it's on ml squared. Wait, but we don't have to use torques or okay, whatever. I mean, at this point, everybody knows how to do it, right? ml squared. So yeah, that's our angular acceleration. There we go. What do you not find actually? You want to find a total acceleration, so multiply that thing by L as well. So I can cancel these away. So that will be A, just the acceleration. Well, I should say it's the tangential acceleration instead. So it's a tangential acceleration. Perfect. Then you want the total acceleration. And also the thread tension. Fine. Thread tension is good. Wow. What's be the thread tension at the moment? So these are the special cases. Angle theta between the thread and the vertical and the momentum and the total acceleration vector of the sphere is given. Okay, these are special cases, whatever. We just find the total acceleration vector first. So, and also the thread tension at different theta values. So you know what the tangential acceleration is. 80 is just g sine theta. Now, what will be the radial acceleration? That's just v squared upon r, right? We don't know what v squared is. Oh. At this point it was 0, so you can just use conversion of energy to get it done. So like this angle is theta, this is 90 minus theta, this is L, so this whole thing will be L cosine of, sorry, this thing, so L sine of 90 minus theta, which is L cosine theta, right? So it has gone down by L sine theta, so you can say, okay, GL sine theta, that's equal to, so like 2GL sine is equal to V squared. That should do it. So V squared upon L, that will be 2G sine theta. Perfect. So yeah, that is 2G sine theta. This is weird, isn't it? Yes, it is. It really is. Am I sure I did it correctly? Oh, I didn't. This thing is 90 minus theta. Sine of that thing, that will be L cosine theta. Why did I take L sine theta over here? It should be L cosine theta, damn it. Okay, so it's gonna be G cosine theta right there. Ah, as expected, something must have gone wrong. That's the usual. Fine, so now you got it. You can figure out what the actual whole A vector should be. A vector will be just this thing. So G times of sine theta, theta hat, right, plus, so theta hat is such that it's along the acceleration, the tangential acceleration, to say that, yes. So for example, right now theta is positive and theta hat is in this direction, so it's along the decrease of theta. That would make sense. And then theta is going to be negative at some point, or you could just do negative theta hat if that bothers that much, right? And what's the radial acceleration? These things like 2 cosine theta r hat. Oh no, instead what we'll do is we'll write this as negative g into 2 cosine theta r hat plus sine theta theta hat. That should do it. So now you got the acceleration vector in terms of theta. You can figure out what tension is, right? So what's the equation for this? It's going to be T. It's like in that direction first. The tangential acceleration, that's not, so tension is not involved in that. It's just the mg force. The thing that it is involved in is it's the centripetal acceleration. It's like tension is equal to mg plus the centripetal acceleration, like the radial acceleration, whatever, magnitude wise, of course. So this is going to be tension is equal to, sorry, m times m. So m times of g plus that's like mg into 1 plus 2 cosine theta. So these two are the equations that you would need. Cool. So there we go. A is done basically. Okay, let's go to B. What do they want? Right. Thread's tension at the moment when the vertical component of the sphere's velocity is maximum. Right. Thread's tension at the moment when the vertical component of the sphere's velocity is first thing first. When the vertical, so wait, what vertical component you say? Oh no, this is bad. Well, we do know what v square was, right? So the radial component that had to do with it, just v square upon r, exactly. Right. So what was it? V squared must have been equal to 2lg cosine theta, right? Exactly. That's v squared, of course. Got theta in this direction, you got v in this, right? This angle will be with the vertical theta, is known as theta. What's the vertical velocity? The magnitude, that is, it's going to be v cosine of this angle, so it's going to be sine of theta. Yeah. I guess that makes sense. Okay. Yeah, that should be the thing. It's supposed to be cosine. Oh, sorry, sine of theta because cosine of minus theta. So v sine theta. And since you want magnitude to square this first of all, so you just got v squared sine squared theta. When is this thing maximum? That's what they are asking. In terms of theta, of course. The v squared is just this thing. So they are basically asking like when is 2lg cosine theta sine squared theta maximum? So, oh come on. Are you serious? It really is like that, huh? I never expected it to be like that. Fine. Let's try to do this thing. So, okay, you can add sine to it and stuff. No. Let's take the derivative and make it equal to 0 something like that. So, what we want is d upon d theta of cosine theta sine square theta. Oh, come on. Sine square theta to be equal to 0. So, taking a derivative, it's got negative sine cube plus 2 sine cosine squared is equal to 0. This should happen, I guess. So either sine is 0, which makes no sense because at that point it should be the minimum velocity, not the maximum velocity. Other case will be there's got negative sine squared plus 2 cosine squared is equal to 0. That just means, well, okay, add 1 on both sides. It's got 3 cosine squared is equal to 1. So cosine squared is equal to 1 upon 3. So whenever that happens, you'll have the maximum velocity. And this of course just means sine squared is equal to 2/3. So what do we want? We want the stress tension at the moment when the vertical component sphere's velocity is maximum. So the tension, that will be this, where it go? Mg into 1 plus 2 cosine theta. It's going to be mg into 1 plus, okay, so cosine theta, fine. So like 2 upon square root 3. I have no idea why I'm getting square root 3 over there. Oh, come on. Did I go wrong? Or did I go wrong? I don't think so. And yeah, like L cosine theta, that must have been how much it went down, and initially it was 0, so it does work, right? No problem with that, right? So then why am I getting 2 upon square root 3? Not something nice. Fine, whatever. You got the thing, huh? Just checking it once again. Yeah, seems good. So it really is like that. Just put it there. Okay. This is your answer. Mg into 1 plus 2 square root, 2 upon square root 3. Fine. Let's go to the next question. So C. The angle theta between the thread and the vertical at the moment when the total acceleration vector of the sphere is directed horizontally. Oh, so okay, fine. Total acceleration of the sphere is directed horizontally. This is bad, really bad. Uh, Wait, what? So you'll have to write this in terms of x and y. Oh god, no. Okay, let's do it. R hat will be this thing, so it's got theta in this direction. Let's call this thing as I hat and this thing as j hat. I know, not what we generally do, but we'll call it like that. Right. So R hat is in this direction, so you can say R hat is just j hat cosine theta plus I hat sine theta, and then what will be theta hat? So theta hat is in this direction. No, it's supposed to be in that direction because we had that negative and everything. Remember? Exactly. So you got it in this direction. This is supposed to be theta as well. So then that will be, so this is I, and that's why this will be cosine and I hat, and then negative sine theta and j hat. Alright, cool. Now, what do we do with it? What we want is this to be completely horizontal. So, your these components, these must cancel out. So, cosine theta times, so let's look at this thing. So, for r hat, you have this times cosine, that's like 2 cosine squared, okay, minus of sine squared, that should be equal to 0. Isn't that what we're saying? Yeah. Fine, let's just like add 1 on both sides because 3 cosine squared is equal to 1, so cosine is equal to 1 upon square root 3. Exactly the same thing as we got before. Yeah, that's when this happens, when it's completely horizontal because there's no j component. Yes. And that was like 3 cosine theta sine theta for the I hat component over there. Makes sense? Fine. And what do we need to figure out? The angle theta. It's going to be cosine inverse. In fact, maybe it's like plus minus cosine inverse because, yeah, both of these, they have the same thing, right? Huh. Yes, so. No, wait, theta is pi by 2, but then it's 0, and then it's supposed to be negative. But hey, theta is a sign, it's not a sign quantity, it's just positive, so you could just say this thing. So cosine inverse of 1 upon square root 3 should be doing it. Next question. 86th. Ball suspended by a thread swings in vertical plane so that its acceleration values in the extreme and lowest positions are equal. Ball suspended by a thread swings in the vertical plane, acceleration values. What in the extreme and lowest positions are equal? Fine. Find the thread deflection. Wait. You are saying those accelerations are equal. Actually, yeah, I mean that's obvious because mv squared upon. Oh, yeah. So like, I understand what's happening. So our tangential acceleration right there? No. There is no tangential acceleration because gravity is just pointing either down or up. So no way for it to have tangential acceleration. This is weird. Oh, okay. I think it's different. So when they say extreme, they mean it is not making a full circle. Instead, it's just doing like this. Oh, yeah, that makes sense. So, hey, it's the same thing as this, except it's not 90-degree directly. So, slightly different. Yeah, but the thing is that where did it go? 86th. Right, acceleration over here, that's just the tangential acceleration. There's no radial component, whatever. And over here is the radial component. There's no tangential acceleration because, yeah, like g sine theta is 0. Huh. Right, so these are somehow equal. That's what they're saying. If this is v velocity over here, then let's say this thing is r. Like v squared upon r, this acceleration is equal to, so if this angle is like theta critical, or let's just say theta naught, which is the largest angle, this will be g sine of theta naught. It was just that, right? G sine theta. Yeah, like this mg sine theta acting on this thing. Think. Yes, that is mg sine theta acting on it, and that upon ml squared. Sorry, mg sine theta times l upon ml squared, and that times l. That will be the actual term, which is in fact g sine theta. That makes sense. Okay, cool. And we also know how to figure out what v is. So what will this complete height be? So this thing is just, this is 90 minus theta, right? This thing is theta naught. So what's this gonna be? This is r theta naught, like r cosine of theta naught. This building is just r. So this is r into 1 minus cosine theta naught. So you can say, okay, v squared. So initially it was at 0. So v squared is equal to 0 squared plus 2 times of the also, yeah, like 2gh, that should do it. So this thing, right? So 2r into 1 minus cosine theta and theta naught, whatever, the times g, that should do it. Just put that in there. So what you get, just get 2 into 1 minus cosine theta naught is equal to sine theta naught, right? That's what we're getting. So 2 is equal to sine theta plus 2 cosine theta, S and C. Right, what do you need to figure out? 86. Find the thread deflection angle direction position. Exactly, that's what we're figuring out. So, oh wait, one is like 2 into, ooh, slightly different than what I expected to be. Oh, we could go like this. Just write it as 4 sine squared of theta upon 2, right? And then this will be 2 sine of theta upon 2, and then cosine of theta upon 2. So sine theta upon 2 gets cancelled because it cannot be 0, of course. Other thing is that, okay, so it just gives us tan theta upon 2 is 1 upon 2. So theta is 2 times tan inverse of 1 upon 2. That should do it. 2 times tan inverse of 1 upon 2. Remember this. 2 times tan inverse of 1 upon 2. And I mean, like, it's 2 times, so you could just write it in a different format, right? You can just figure out what sine theta has to be. Yeah, we could do that, you know. So that's this thing is just theta. What else is it? Like, this can be written as let's go with cosine. So cosine inverse. No, let's go with sine. Sine inverse of, so 2 times of this thing is just 1 upon minus 4. That should do it. So sine inverse of 4 upon 3. That should do it. This is better. We'll write it like that. Oh wait, okay, this makes no sense because, oh yeah, this definitely doesn't make any sense. It's supposed to be 1 plus d squares, like, sorry, 4 plus 1, 5. Hey, is that for real? It really is like 4 upon 5? Oh, come on. What was the equation once again? 2 into 1 minus cosine is equal to sine or something. So 2 is equal to sine plus 2 cosine. Does this work? Sine is equal to 4.5, cosine is equal to 3.5. If the, yes, it does work. Huh. That's weird. I'll just come out. That's nothing. So it really is just that. Sine is 4.5. Okay, which is like what, approximately 53 degrees, 3.7, I think, whatever, 3 degrees, like 54. I don't know, I don't care. Let's go to 87 now. A small body A starts sliding off the top of a smooth sphere of radius r. Find the angle corresponding to the point at which the body breaks off. Hey, this is like a staple question I've seen in some exams. Every time it just trips me up, like how to solve this. There is a break off. So let's do it once and for all. So this is a spherical surface. You got a small body on the top of it, and it's falling down, right? So whenever this makes, let's say, angle theta with the horizontal, so initially it's making 90 degrees. right? This body is making theta. Then you got a normal force. You got mg sine theta in this. This is of mass m, that is. So mg sine theta, I guess. No, it's supposed to be cosine theta because, yeah, it's cosine theta, right? I mean, like this angle has to be theta. This has to be that, of course. This has to be theta. So mg cosine theta, and this has to be right other angle. This thing that has to be mg sine theta. Wow. Fine. If this is moving with velocity v, of course, in this direction, the tangential one, then what can you say? Well, first of all, let's write some equations. We got mg cosine. It's like g cosine theta. That thing is dv upon dt, right? It's the tangential acceleration. And wow, this is weird. And what else? So the normal force is equal to so part of it is used and the other part has to be described by normal force. So it's going to be mg sine theta minus minus the centimeter acceleration, which is mv squared upon r. So instead of using v, we'll just say why not use omega. Yeah, I mean, why not? Because then you can write this thing as r d theta upon dt. Sorry, d omega upon dt. That should be nice, like r alpha. And over here, this will be m omega squared r. Cool. So now we need to figure out at what theta this will break off. Well, when this breaks off, what actually happens is that this normal force is no longer is no longer sufficient to what do I call it? Sorry, it's no longer needed. That should be the thing. It's no longer needed. That is, this value will start becoming negative, which is like impossible, of course. So this will break off. So the breaking point, maybe I will call that as phi. That will happen when you have g sine phi is equal to omega squared. So at phi, right, whatever that point was, times r. So first of all, we need to figure out what omega squared is. So from this equation, you can say, okay, this thing is just omega d omega upon d theta. So integrating that, you get g sine theta is equal to r omega squared upon 2, and it goes from where to where. So initially it's 0, and over here sine theta, initially it's just 1, you can say. So you can write this as g times of 1 minus sine 0 something. Yeah. Oh, of course, it's supposed to be negative. Like this is supposed to be negative d theta upon dt is omega, right? Exactly. Omega will now be negative d theta upon dt. That should be it. Then derivative of that things like alpha is also just negative d square theta upon dt square. That's why it's. Or you could say this. That will make perfect sense. So in this case, you would say, okay, omega is d theta upon dt, but instead of writing this equation as positive, we'll write this as negative. So then it will be 1 minus sine of theta. Sorry, sine of phi. I should do it. Or no, you know what? Let's do it for the general thing. So we'll just have this equation. No, okay, no. Right, phi right there. Right, the critical angle and everything. And now we'll just divide this. Exactly. So like 2 over there. Dividing this, you just get what sine phi is equal to 2 minus 2 sine phi. That's it. That's all you need to know. So just have 3 sine phi is equal to 2. So sine phi is equal to 2 upon 3. So phi is equal to. It's kind of weird how this somehow turned out to be something that is not even like dependent on theta. Sorry, dependent on. But yeah, this is weird. It's not dependent on how big it is or what gravitation is acting or anything, right? It just is. Wow, this is a result worth remembering, I think. This is awesome, but yeah, it's not like a formula. So how do I make this more general? What we can do is that instead of doing this, we can launch this with some initial velocity, right? So there will be some initial omega naught that this will have. So then it will be the same equations as these, but instead of having omega squared over here, what you will have is omega squared minus omega naught squared, right? That makes it slightly more difficult, I guess. Yeah, and also more difficult to figure out what this has to be. Then you could do this, and then it will depend quite a lot. So the same thing as we did before. So 2g into 1 sine phi plus omega naught squared r is equal to omega squared r, and then this omega squared r is equal to g sine phi. And from here you can figure out what phi is, because you will know what omega naught is, what r is, what, like, yeah. So just solve this equation, you will get your phi as a general value, right? At what angle will it break off with, and this angle is of course the one that it makes with the horizontal. Let's try to solve this. So I'll divide by g on both sides. It's got 2 minus of 2 sine phi plus omega naught squared r upon g is equal to sine phi. So it's got 3 sine phi. What am I writing? Sine phi is equal to 2 plus omega naught squared r upon g. So divide by 3. There we go. So yeah, like phi will be sine inverse of 2/3 plus omega naught squared r upon 3g. This should do it. Now this is something worth remembering. And in the case when I just, yeah, omega naught is 0, this will be sine inverse of 2/3. Yes. Hey, and by the way, what do they want? They want 37th angle theta, correct? Oh, so it's like 1.2, but they even gave us a figure. Oh, this angle is what they want. So fine. So it's supposed to be cosine inverse. So this is something worth remembering, right? So instead of writing sine inverse, I'll just write cosine inverse, because this is the complementary angle of that. Cool. 87th done. Let's go to 88th. A device 1.26 consists of a smooth L-shaped rod located in a horizontal plane and a sleeve A of mass m attached by weightless springs to the point B. Okay, the spring sorry, wait, what? It's a sleeve A. What does that even mean? Oh, so this is like the rod, and then on, oh, so fine. This bolt, it has a spring attached to it. Fine. The spring stiffness constant is equal to x. The whole system rotates with a constant angular velocity omega about a vertical system passing through the point O. Find the elongation of the spring. How is the result affected? Wait, what? So the spring is, it's rotating like that, huh? It's a sleeve. So weightless spring to point. So this spring is attached at point B, not at A, to the rod. Okay, cool. Okay. Understand what's happening. So like this whole, so this guy A, it's just rotating in a different circle then. Okay. By the long shot, how is the result affected by rotation? So they didn't give us the dimensions. Why? Do we not need the dimensions? Oh, so let's do it. Maybe we really don't need a dimensions, whatever. So we just say this thing is R, and then you can figure out the, yeah. So what forces are on A? There will be, so think about it. You got this point O, you have this B and A stuff. So now this rod can put forces in directions like these. It cannot put in this kind of direction, because yeah, I mean, what do you expect of it? Friction, seriously? So that won't happen. Okay, I understand that. uh Fine. You know that this A, it experiences the total acceleration of this thing is in this direction, right? There's this force that is a component of it, and then there's the spring force. Exactly. So it's just two components that make up everything. I mean, of course, there's gravity and everything, but we'll ignore that for the moment, right? I mean, that's cancelled by the normal force term on. Don't do that. So really, it's like its vector decomposition. It's just the spring force plus this normal force. So we can figure out what the spring force will be. Easy, really easy. Given you know what dimensions it has, but they didn't give us the dimensions. So they give us the constant angular velocity omega, okay, but no dimensions or whatever. Okay, fine. So we'll just say this thing is, I don't know. We'll call this thing as A, this thing as B. Nah, we'll call this thing as R. And we'll call this angle that it makes as, or maybe like this angle is what we should call as theta, right? But most likely that's not how they will present it. So maybe they will just give us what these lengths are, or one of what these lengths are. Fine. So I don't know, maybe they gave us what this thing is. It's capital R. Or no, let's say this thing is small r, this thing is capital R. And this thing is, I don't know, we'll call it something small a. No, but we use a for acceleration. Doesn't matter. In the end, we won't have acceleration equations. So what is the cerebral acceleration for this guy? It's just gonna be omega squared r, and that is provided by this plus that. So this guy's component along here. So this angle theta, that's what we use, right? So this will be the cosine theta of this thing. Isn't that correct? Yeah, I guess that's correct. That's equal to k times x. So from here we can figure out what the compression, oh sorry, elongation, because the thing is, it's pulling, so it has to be elongated, right? So x will just be equal to omega squared r upon k times cosine theta. Now what do we do with, so like what's r cosine theta? It's just equal to this. This is awesome, isn't this? It's just awesome. Yes, it's just a, wow. So it's just omega squared a. Ha, perfect. Right, so if AB is of length small a, then this is just omega squared a upon k. Or let's say this is of length L, right? This thing is length L. Because I don't know, if you're going to use this ever in another question, it will be better if I just use L. Cool. There we go. Got the elongation. Omega squared L upon R, where, oh, it's supposed to be 1k. Sorry. Wait, so it wants what? Elongation of the spring. But okay. Yes, spring constant. We can find what the strain on this spring is. Yes. But for elongation, okay, the better way would be to whatever, just do it. Where L is length. Okay, whatever. L is equal to AB. That's it. Next. So even if the spring is not attached to B directly, but somewhere else, yeah, you can still do the same thing. It's gonna work. Let's go to 89th. Okay. The cyclist rides the cyclist along the circumference of circular horizontal plane of radius r, the friction coefficient being dependent only on distance small r from the center. horizontal plane, okay, circle of radius capital R, cyclist on this, okay, friction being dependent only on the distance small r from the center O of the plane as this thing. Wait, what are you doing? It's just along the circumference, right? Then why are you doing this thing? Huh? Find, okay, where can also constant. Find the radius of circle uh, with the center at the point along which the cyclist can ride with the maximum velocity. What is this velocity? Okay, the maximum velocity is this velocity. So fine, let's try it out. First of all, what's the centripetal acceleration? So v squared upon capital R. So over here, what we'll do is instead of this, we'll just have small r over here. So the plane is of radius capital R, yeah. But wait, but it does say it rides along the circumference of the circular horizontal plane. How small are center at the point along which I don't get it. It's putting two different contradictory statements together to, I mean, okay, you already said it's along the circumference, and then you are saying it can also ride with small r less than capital R. Oh, come on. This is weird. But hey, I understand what we're trying to do. So let's do it. So if this is small r, it's starting with small r radius, then it's the v squared upon r is equal to the centripetal acceleration, which is completely provided by the friction. So how do we do that? What force will the friction put? It is going to be mg times uh, times the friction coefficients, mg times k. That should do it. So one thing is that this cyclist, this cycle has wheels, right? Obvious. It's not, this guy is not changing its velocity, right? So the whole system as like the cycle plus the cyclist himself, that system is not changing its velocity, so sorry, the speed, and that's why there should be no tangential acceleration. So friction does not act in any of these directions. It only can act in this or this direction, and of course it acts in this direction because centripetal acceleration is required and everything. Right, that should do it. That should do it. Okay, cool. So this is just mgk, yeah. So when will your v be maximum? So like v is related to small r, like this v squared is equal to mg times small r times k, but we know k is just this whole thing, so like it's k naught into small r minus small r squared upon capital R, right? So when will this be maximum? That's what we want, right? So its derivatives like 1 as 2r upon r, that should be equal to 0. She's got small r is equal to capital R upon 2. That's when it can happen. Finally, it's a circle with the center at the point along which the cyclist can ride with maximum velocity. It's doable. So just capital R upon 2. Also, what is this velocity? And the velocity will be, so like when you put that over there, just get, what do you get? So small r is capital R upon 2, and that times 1 minus small r upon capital R, which will be 1 minus small r upon 2, so like it's 1 upon 2. Cool. So yeah, it's gonna be what? Square root of mg k naught r and that whole thing upon 2. That should be doing it. Next question. 90. A car moves with constant tangential acceleration, this thing, along a horizontal surface circumscribing a circle of radius r is equal to 40 meter. Fine. Motion of friction, sliding friction between the wheels of the car and the surface is this. Fine. What distance will the car ride without sliding if at the initial moment of time its velocity is equal to 0? So without sliding, you say. Hmm. This guy's mass is not given, right? Hmm. Okay, think about it. It's going along a circle itself, and then the wheels are also rotating, and the thing that is rotating the wheels is this friction, of course. So if it's just pure rolling, then nothing much will happen. But okay. I don't get it. I don't get it. Oh, it has a constant tangential acceleration. I should have read that. Fine. So forget about the wheels. What? Fine. I know this is actually very much complicated because the thing is that the wheels are in fact stationary with respect to ground. Because like the contact point is stationary. That makes sense, right? So there is friction. There is friction pointing inward, as we saw before, and then there's this tangential acceleration which cannot be pointed by friction itself. So, right, that's also coming from the friction itself. Oh, come on. Fine. Let's try to do it. So, tangential acceleration given. So what's the total frictional force, the magnitude that is? That's what we need to figure out. So just have omega is equal to, wait, you just give us the acceleration, not the angular acceleration. So your v, that will be r times omega, sorry, r times of this wt. It's supposed to be w. Okay, cool. And v squared upon r, which is basically just this thing squared upon r. It's like w squared. Wait, what's this? Sorry, it's not supposed to be like that. T times of this. That should do it. Sorry. So v squared upon r, that will be this thing squared upon r. It's like t squared, w squared, t upon r. Right. That's the centripetal acceleration. Cool. So then, what distance will the car be able to slide without sliding? So yeah, ride without sliding. Hmm. Think of something else. Why don't we go? Why don't we use this equation? Maybe that's better. So we'll just have v squared is equal to whatever distance is traveled that times the initial acceleration. That should do it. So just w times, so the distance traveled, call this d, and then v squared upon r, that will be w t upon r, which is basically like w theta, but whatever. This should do it. Fine. So it's supposed to be 2wd, but yeah, makes sense. Okay, and what we want is that the friction force, magnitude of the friction force, capital F, that will just be equal to 2wt. Wait, it's supposed to be square of that upon r. That's just the acceleration. That's not what we want. And this thing is, it's not even what we want. Yeah. Sorry. So the frictional acceleration, you can say that, right? The total acceleration of this thing, which is also the frictional acceleration, that will just be, come on, why am I waiting out the post? It's just F is equal to m times acceleration is square root of, so this whole thing, and then w, that should do it. So for that, you just have mw square root of 4d squared upon r squared plus 1. That should do it, right? And this has to be less than or equal to mg k. Yes, this cancels. So there we go. Right. And what distance will this car travel with without sliding? So you got it. You just need to find at what t will this be equal to, will this inequality be an equality? Exactly. So it's got 4t squared on r squared is less than or equal to squaring this, got what, g squared k squared upon w squared and then minus 1. That should be it. So you can say, okay, d squared is less than or equal to r squared upon 4 into g squared k squared upon w squared minus 1, right? So for this to keep on going, what must happen is that d should be less than or equal to that. But we just want to figure out what's the critical one. So r upon 2 square root of g squared k squared upon w squared minus 1. So time to figure out what this is going to be. What's gk upon w? Well, that was the thing, right? It was absolutely, that was the thing. So what's gk upon w? K is 0.2. That times g, which will take to be 10. That upon w is just 0.62. Cool. So basically 2 upon 0.62, which is 1 upon 0.31. So it's going to be 100 upon 31. And then this minus 1 and all that stuff. So like supposed to be r upon 2. Come on, why are we doing this? Square root of 100 minus 31 is just got 9 right there, and 7 minus 3. Sorry, 9 minus 3. 669 upon 31. Fine. That's like a multiple of, I don't know. It's like 3 times of 23. Doesn't work. That's it. We'll have to leave it like that. Oh wait. I think we left up something. Oh yeah, it's supposed to be squared. Of course, squared. This will be 69 upon 31 into, so this plus 1. It's like 131 upon 31. So this will be r upon 62 square root of whatever this is. 69 to 131. Can we parameterize that? 69. Oh wow, this is, I don't know, I've never seen this before. 69 is 3 into 23. Is this also multiple of 23? Maybe like 7, so this is 14, and no, doesn't work. Fine, you just have to leave it like that. And by the way, what's r? 40 meters. So 40 upon 52, it's like 20 upon 23. Sorry, 20 upon 31. What am I saying? 20 upon 31 square root of 69 to 131. I'm not even going to calculate all of this. Just leave it like that. Okay, so this is it, 90. So yeah, fine. I'll see you guys in the next video. Bye.